Section 2.5 is the chain rule. So this is one of our probably the most important derivative calculation rules of all so far. It's used very commonly, and it's really sort of an integral rule because it allows us to take the derivative of the composition of two functions. And since so many functions can be thought of as a composition of functions, we can apply this rule to functions in those classes, right? It means that this is a pretty widely applicable rule for finding the derivative of a function. Now, the hard part is to realize exactly what is being composed in terms of two functions, because we're not told that, given a function at random, that what an outer function f is and the inner function g is. So we had to sort of spot that for ourselves, but the chain rule works as follows. If we're looking for the derivative of f composed with g of x, or another way to say this is f of g of x, or I could even write it as f of g of x, then the derivative of that function, it's not, you might guess it's f prime of g prime of x. It just turns out that that's not true, right? And we see below what that chain rule actually is. It's the derivative of the outer function f, so f prime here, applied to the inner function. So we keep the inner function in f prime's argument as is, and then we multiply everything by the derivative of the inner function. And of course, this will work for three layers of functions as well, right? If we had an h of f of g of x, it'll be h prime of f of g of x times f prime of g of x times g prime of x. It would work down the chain like that. And we'll see that towards the end with some examples. So another notation instead is this, or I put here as follows. We can take the derivative of the outer function and then multiply by the derivative of the inner function. Yet another way to see it. Now, I'll do a lot of these by substitution. We'll see perhaps the two different examples of this in this page, and then as we go, you can kind of think about doing any of the examples that I do without the substitutions that I suggest here. I just use the substitution, namely u is equal to g of x, so that I can more cleanly deal with the derivative of the outer function that appears. So we're asked to calculate the derivative of capital F of x equals square root of x squared plus 1. So sometimes it's hard to spot the outer function, the last composed function, f, lowercase f in this case. And in a situation with a root function, it's sort of easy, right? The square root's the outer function, right? In some sense, it's the last operation we do after doing x squared plus 1. So f of u, our outer function, is just the square root function of whatever we place into the argument. Now, of course, this is f of x squared plus 1, where u is x squared plus 1. If we translate that from the above. So what we've done now is we've split the two functions apart from each other. So what I know I need is the derivative of the outer function. So I need to find the derivative of u to the 1/2, which is the same function as square root of u. And by the power rule, that's 1/2 times u to the negative 1/2. So we've got f prime of u. So what we'll do is we'll keep hold of that, or keep an eye on that. We'll use it in a moment. And we need to look at u here and realize that we need to find g prime of x, because we're going to use g prime of x as a multiple times f prime of g of x. So we'll calculate u prime, and that comes out to 2x, of course, because we use the power rule, differentiating this polynomial x squared plus 1. So our function capital F of x is equal to lowercase f of u. And well, by the chain rule, we can write the derivative of capital F as f prime of u times u prime. In other words, f prime of u times g prime of x, possibly, right? In this case, I just kept it all as u's. And then we can just put the pieces together. We know that f prime of u is 1/2 u to the negative 1/2 times u prime. But all of this is still in terms of the variable u, and we really actually want it in terms of the variable x. So now we can start to back out of this substitution. For one thing, I know that u prime is equal to 2x. So I can replace u prime with 2x. Also, I know that u is equal to x squared plus 1. So in a subsequent line, I'll replace u with x squared plus 1. And now we just simplify the terms that remain after we've converted everything back to the x variable. And that comes out to x times x squared plus 1 to the power of negative 1/2. So similarly, we can avoid that u substitution altogether. That's not really necessary. It's just it's a way to spot these pieces and how to help students identify the outer function and take the outer function's derivative. But once you start to get the hang of it, you don't really need that. We could think of it in these terms. The outer function is just the root function of x, right? F prime of x is 1/2 x to the negative 1/2. That's the derivative of x to the 1/2, right? Or the root function of x. And g prime, or g of x being x squared plus 1, it has derivative 2x here. And the way we can put this together is just to say, okay, f prime, this function of g of x. So f prime of g of x means that rather than having an x here, I'm going to have the whole g of x function, which is x squared plus 1. So that looks like this. Here's f prime of x squared plus 1. F prime is 1/2, whatever is in the argument of f prime to the negative 1/2. In this case, g of x is in the argument, and g of x is x squared plus 1. Then times g prime of x is just times 2x. And again, that simplifies to this situation. One last way we might see this, the simplest possibly, is to look at x squared plus 1 and think of it as follows. This is raised to the 1/2 power. If I take its derivative, I'm going to use an arrow just to indicate the operation to derivative. It's not standard. This is just shorthand for the moment. I think about applying the power rule to the outer function. So I have 1/2, and then x squared plus 1 to the negative 1/2. Right? The power rule says to subtract 1 from the exponent. And then I multiply by the derivative of the inner function, 2x. And there's the same thing all in one line. And that's typically how we'll do these, but most of these examples are lined up to be done in with these u substitutions, just to be clear on which part's which. So another example, we're asked to find the derivative of y equals cosine of x cubed. Okay, cosine of x cubed. So the outer function is cosine of u, so f of u is cosine u. F prime of u, so the derivative of that outer function is negative sine of u. And we have that the inner function is x cubed, so we call that u or possibly g, and u prime is 3x squared by the power rule on that function. So when I put it together, I'm going to have f prime of u times u prime. I know that f prime of u is negative sine of u times u prime is 3x squared. And then the last thing I need to do is replace this u with its function of x, and that's x cubed. So I have negative sine x cubed times 3x squared. And there's that answer. Again, to do this in the more shorthand version, maybe I'll put it off to the side here. I would say y prime is equal to negative sine, the derivative of cosine of x cubed, right? Leaving the inside untouched, times the derivative of the inside x cubed, which is 3x squared. And that's a similar way to arrive at it. We could rearrange terms and have the exact same answer. So that's maybe probably the more practical way. Doesn't show the student, doesn't show you as well how to do it or what's going on with it, but ultimately that's what you'll end up doing once you get used to using this rule. Okay, now y equals cosine cubed of x. Notice this is different than cosine of x cubed. And the second function, we're cubing the result of cosine. We're not taking the cosine of x cubed. So this notation really means the following, that we cube cosine of x. So the outer function now is actually this cubing function. So u cubed. U is cosine of x. The inner function, the derivative of the inner function is negative sine of x. F prime of u is 3u squared. Right? In other words, just do the power rule. 3 comes down as a product, and the new power is 2. So anyway, y prime comes out to, again, same formula every time. F prime of u times the derivative of the inside times u prime, or f prime of g of x times g prime of x. Now in this case, f prime we've seen is 3u squared. There's that. And then g prime of x, or u prime, is negative sine x. We've already had. And so we've got this line complete. And then the last thing we need to do is look at u and realize that u is cosine x. And that swaps in for 3u squared here. And then simplifying this, we have the line at the bottom. So again, hopefully the substitution helps to clarify. If not, and if you already see the the method without making the substitution, the assignment of u to the inner function, then that's fine. And if you're consistently getting things correct, then that's the way to go. There's nothing to worry about. You don't really need to use this u substitution. After this section, I'll probably drop it. And in fact, I probably shouldn't call it a u substitution because that's sort of a designated term in Calc 1 in an informal way. But nonetheless, let's keep going here. We've got the derivative of each function here. So we've got some power function of a polynomial. All right, so clearly the inner function is this polynomial. The outer function, we're raising whatever, raising something to the power of 20. So each derivative is pretty easy to get. This is from a power rule to get u prime. And then u to the 20th is 20u to the 19th. So this really makes this nice, right? If we think about this back in terms of how a product rule must work, this could be an absolute mess if we had to go that route. So with the chain rule, it really cleans it up, right? So y prime is the f prime of u times u prime. So here we have that together. And then we just back out of these substitutions. U is x cubed minus 4x. So here's that replacement. And then u prime is 3x squared minus 4, and there's that replacement. And again, f prime of u is 20 times the argument and then to the power of 19. So here's our complete derivative here. That's really a nice shortcut for things like this, because usually a binomial raised to a 20th power, that would be a huge algebraic expression, right? So it's really nice that we have the chain rule to help us calculate that derivative, and we get it, and really we could do this as a one-line derivation, right? We could just look at it and say 20 times x cubed minus 4x to the power of 19 times 3x squared minus 4, and that's everything we see right here. And really, we'd have that derivative in one line thanks to the chain rule. So that's a pretty powerful use of it. Now, f of z is this rational function, 1 over z squared plus 1. The trick to this one, we could, if we like, use the quotient rule, right? We saw that last time. We have the quotient of two functions, in this case 1, and then the other function z squared plus 1. Then we could use the quotient rule. Another way to view this, since this is just a 1 here, is we can view this as the reciprocal function. So z squared plus 1 to the negative 1, right? And now we've nested it. So this is raised to a power of negative 1. Our outer function is this u to the negative 1 function, which has derivative thanks to the power rule, negative 1 u to the negative 2. And then the inner function u, which is z squared plus 1, has derivative 2z. And now we're ready to put it all together as usual. F prime of z is the derivative of the outer function at u times u prime. So that's negative u to the negative 2 times u prime is 2z. And then what is u? U is z squared plus 1. So we have negative z squared plus 1 to the negative 2 times 2z. And then we rearrange the terms and clean it up a bit to look like that. So here we have it. Reciprocal functions can be thought of as in a composite way rather than as a quotient, if we like. So calculate the derivative of this function, f of x equals sine of x times tangent x. Now they're getting a little bit more complicated. The inner function is x tangent x, so I'll call that u. And then I want to find the derivative u prime of the inner function. Well, I have to be careful now because u is a product of two functions. So I have to use the product rule when I take that derivative. So it's the derivative of the first, of x, times the second function, tangent x, plus the first function, x, times the derivative of the second function, tangent x. And with that, I see I have 1 times tangent x, and then plus x times tangent's derivative is secant squared x. So there we go. We have this thing all together. The outer derivative, remember the outer function is sine of u. Its derivative is a little easier. It's just cosine of u. So now I'm going to have f prime of u times u prime, the outer function derivative applied to u times the u prime. So this is cosine u times u prime, which we found above. And then the cosine of u is x tangent x. So cosine of x tangent x, and here's u prime written right there. That's about as simple as this one will get. Probably no need to distribute that. This is pretty sufficient. Okay, and well, as I said before, we can do this for multiple layers, right? And in this case, what I'm going to do is I'm going to use this differential operator instead of all these u substitutions. This might actually be even more clear for students. So maybe you prefer this method. So the way to go about doing this is we pass this operator into our nested functions or our composite functions one layer at a time. So I take the derivative of the outer function in this case, that's sine. Okay, the derivative of sine is cosine. And we apply that to the argument inside the outer function's argument, right? And the argument of the outer function, tangent x squared, tangent of x squared, right, is the argument. So there's our outer derivative applied to the inner function. And what the derivative does now, or the operator does now, is it moves one layer in. Now it acts on tangent of x squared. We take the derivative of tangent of x squared, right? This is the derivative of the inner function. Well, when I look at this inner function, I realize, well, it is also a composite function. The outer function is tangent, the inner function is x squared. So then the derivative of tangent is secant squared. I apply that derivative to the argument, x squared. And then lastly, I take the derivative of the inner function here. And that's the product on the end here, right? So I can keep doing this. I could work 4 layers in if I wanted to, if I had 4 composed functions. In this case, the innermost function is x squared. Then next layer out is tangent, and next layer out is sine. So this is actually the chain rule being applied twice. This is the first time, and then this is the second time here. We apply it to that middle layer function, tangent of x squared. And the derivative of x squared is just 2x. So here's our answer to this one. So yeah, I think with a little bit of practice, students get the hang of this pretty easily. Be careful with it. If you find that you are making a lot of mistakes, those u substitutions will help. This is the end of any practical examples that we might look at. I've got a couple problems for students to try for practice. Find f prime of x of this function. So we have 3 layers again, cosine of sine of cosine x. So you could move through this with that differential operator, the derivative of the outer one applied to this function, times the derivative of this function applied to this function, times the derivative of this function at x, right? And we finally get to x as the argument of that third one. So by the way, the derivative of x, we could multiply by the derivative of x at the very end, but the derivative of x is just 1. So that's sort of an unnecessary step in the chain rule. It's kind of always been there for us. Okay, and then another one, g prime of x, if g of x is tangent of 1 over x squared. Or maybe a quick way to write this is tangent of x to the negative 2. So then we don't have to do multiple levels. This is just an outer function with one inner function. That's a little easier. It should be one application of the chain rule. Another interesting little fact that I won't go through is another way that we could have derived the quotient rule would be to come up with the chain rule, and then we could write a quotient f of x over g of x for any differentiable functions f and g as f of x times g of x to the negative 1. And since we know the product rule, we can use the product rule to find the derivative of this product. And since we know the chain rule, whenever we have to take the derivative of g of x to the negative 1, we know how to do that. And namely, that would look like this little term right here. Raise it to the power negative 2 because negative 1 comes down in the power rule, and then multiply by the inner function's derivative. G of x is the inner function. Its derivative is g prime of x. I won't go through the rest of the details. They're not exactly essential, but the interested reader could follow through with that and see that this is a nice way to potentially calculate the quotient rule if so desired. So that's it. Get some practice with the chain rule. That's one of our most powerful tools for taking derivatives, and it's something that we're going to use throughout the rest of this course and really throughout the rest of calculus.